Welcome to The Explainer. All right, today we're tackling quantum computing. And look, let's cut through all the sci-fi hype. We're going to get our hands dirty, look right under the hood, and see how these things actually work, all the way down to the code. So here's the plan. We're going to start with the basics, what makes these computers so different. Then we'll get into the heart of it all, the qubit. After that, we'll actually code up a quantum circuit, check out the mind-blowing algorithms they can run, and then we'll peek into the future.
All right, let's jump right in. Think about the device you're on right now, your computer, your phone. It all boils down to a really simple idea, right? Bits. They're either on or off, a 1 or a 0. That's it. Well, quantum computing basically takes that rulebook and just tosses it out the window.
And this right here, this is the absolute key difference. Your standard computer bit, it's like a light switch. Click, it's on. That's a 1. Click, it's off. That's a 0. Super simple. But a quantum bit, or what we call a qubit, that's more like a dimmer switch. It can be all the way on, all the way off, or, and here's where it gets wild, it can be somewhere in between, a mix of both on and off at the exact same time. It's all about probabilities until you actually check it.
So, you might be asking, why bother with all this complexity? And that's a fair question. These machines aren't going to make your Netflix stream any faster. Nope. They're designed for a whole different class of problems. The kind of stuff that would make today's biggest supercomputers just give up. We're talking about things like cracking modern-day encryption, designing brand new drugs by simulating molecules, or solving ridiculously complex logistical puzzles. Okay, so we've got this dimmer switch idea. Let's peek behind the curtain a little and see how the math works, because that's where the real magic happens. Now, don't freak out when you see this equation. I know it looks a bit intense, but the idea is actually pretty straightforward. All it's saying is that the qubit state, that little psi symbol, is just a mix of the 0 state and the 1 state. And the secret sauce, it's those alpha and beta values. Just think of them as two knobs that control how much 0 and how much 1 is in the mix. They're what hold all the probability information. And here's the one rule you can't break. If you take those alpha and beta numbers and square them, you get the actual chances of seeing a 0 or a 1. It's really simple, just like flipping a coin. The chance of heads plus the chance of tails has to add up to 100%, right? It's the exact same for a qubit. The probability of finding a 0 plus the probability of finding a 1 always has to equal 1. So, this incredible ability for a qubit to be a mix of both 0 and 1 at the same time, that has a name. It's called superposition. And honestly, you can think of it as its first quantum superpower. This is what lets a single qubit pack in way more information than a simple on or off bit. And it's the absolute foundation for the insane parallel processing power of these machines. Okay, so we've got these qubits that are in this state of superposition. Awesome. But now what? How do we actually tell them what to do? How do we, compute? Well, that's where something called quantum gates comes in. They're basically the building blocks for programming a quantum computer. Yeah, you can really just think of these gates as commands. You've got simple ones like the poly-X gate. It's basically a flip command. It turns a 0 into a 1 and a 1 into a 0. Easy enough. But then you have the Hadamard gate, the H gate. Now this one is pure quantum magic. It's the button you press to put a qubit into that perfect 50-50 superposition we were just talking about. And then you get to stuff like the CNOT gate. It's a 2-qubit gate that connects them. It says, hey, look at the first qubit. If it's a 1, then flip the second qubit. This creates this spooky, powerful connection called entanglement, which is the second quantum superpower. And what's so cool about all this is that it's not just chalkboards in theory anymore. Not at all. We can actually sit down and write code right now to build these circuits and even run them on real quantum computers in the cloud, all thanks to toolkits like Qiskit. So get this. Look at this code. It's just 4 lines of Python, but it's a complete quantum program. So step 1, you import the library. Standard stuff. Step 2, you create your circuit. We're telling that we need 1 qubit and 1 classical bit. We need the classical bit to hold the final answer. Step 3, this is the fun part, QC.H0. We apply that magical Hadamard gate to our qubit. Boom, it's now in superposition. And finally, step 4, we measure it. Now, measuring is a big deal. It's what forces the qubit to pick a side. It collapses out of that probability cloud into a definite 0 or 1. And since we put it in a perfect 50-50 mix, what do you think happens when we run this 1,000 times? Yep, we'll get 0 about half the time and 1 the other half. We just built a perfect quantum-powered random number generator. How cool is that? That little program, that's basically the hello world of quantum computing. But it's just the start.
When you begin to chain these gates together, building more and more complex circuits, well, that's when you start to unlock these game-changing algorithms that can solve problems we used to think were impossible.
So let's talk about Grover's algorithm. Imagine you have a giant, totally unorganized phone book with a million names, and you need to find one specific number. Your regular computer? It has to go through it one by one. Could take up to 1,000,000 checks. A quantum computer, running Grover's algorithm, it can find it in about 1,000 steps. That's not just a little faster, that's a quadratic speedup. It's a total game changer for searching. Okay, Grover's algorithm is impressive. But Shor's algorithm, it's on another level entirely. I mean, the quote here says it all. It breaks RSA encryption. How? Well, most of our online security relies on the fact that it's incredibly hard for classical computers to find the prime factors of gigantic numbers. Shor's algorithm can do that, exponentially faster. It basically finds the secret key. This is the one that keeps security experts up at night, and it's the reason there's such a massive global race to build these things.
So this power is obviously incredible. But let's be real. You don't have a quantum computer in your laptop. Why not? Because qubits are unbelievably delicate. They're super sensitive to their environment, which causes a lot of errors. So that leads to the big question. Where are we actually on this journey to a quantum future?
I mean, just look at this chart. The progress is nuts. We're deep in a full-on qubit race. If you just look at what IBM is doing, they went from about 100 qubits to over 1,000 in just a couple of years. And that's happening everywhere. The sheer number of qubits, the raw power, is just exploding. But, and this is a huge but, the number of qubits isn't everything. It's all about quality over quantity. The next giant leap is getting a handle on all those errors. And as you can see on this timeline, the big goal is to get powerful error correction built in within the next few years. That's the stepping stone to what we call fault-tolerant quantum computers, which experts think we might see in the 2030s. Those are the machines that could reliably run something as demanding as Shor's algorithm. So this all leads to a really fascinating final thought. As we keep building bigger and better machines, is the future just about better engineering? Making more stable qubits, perfecting error correction? Or is the next massive breakthrough going to come from somewhere else entirely? Maybe a whole new discovery in math or a deeper understanding of quantum physics itself. Whichever it is, the answer is going to shape the future of technology and science as we know it.